Okay, first announcement. Review session has been determined Wednesday at 2:30 in Bishop's main lecture hall. Today what we'll do is just go over parts of problem set 6, and then I will work on some of the multiple choice, get that up hopefully over the weekend, if not first thing on Monday, and then we can start reviewing. So for problem set 6, I've made a few changes. There are a couple of problems that pretty much will just, they're fun to do, but it's not really that important. So do not do number 3 nor number 6. And I'll make a note of it in an email. For problem 1, it talks about a velocity selector. Now what I did is, this is the general just unit play to get velocity out of it. You know that the force on a charge is Q times the E field. Force on a wire is also ILB. So if you solved for E and B and started playing around with the units, you can extract meters per second. So you can see how that works. A velocity selector, we haven't really talked about, but this is the setup. When we talked about the particle spectrometer, these particles had an initial velocity in a B field, and due to their charge and mass will bend in a particular direction. There is something called a velocity selector. This will only allow particles of a specific velocity to pass through. When a particle is, let's say, positive, and then in another example we'll do negative, it's moving with a velocity v. Now in reality, a whole bunch of particles have a whole bunch of different velocities, but this is just a generic single particle. What we do is we set up an E field. Could be left to right, right to left, doesn't matter. But the negative and positive particles are always moving along together. So if a positive charge sees an E field from right to left, it will feel a force Q times E to the left. Negative particle on an E field in that direction, its force is also Q times E. Now what I'm really interested in are the magnitudes of everything and letting logic dictate direction. The other thing that we do is, in this pipe, and let me see, V, this is it. The B field has to be in a particular direction. And in this case, it will be up. For a positive particle moving in that direction, V cross B causes a magnetic force to the right. Now, V cross B for this negative particle is also to the right, but because it's a negative particle, it goes to the left. So regardless of the charge, if it's positive or negative, the B field can be in the same direction, but the B field is set up so that the magnetic force is opposing the electric force. What we do is we look for the situation where the sum of the forces in X is 0. So it doesn't really matter about the sign. All that matters is that they're opposite. FB minus FE, FE minus FB, it doesn't matter because FE will equal FB. Now the force of a charge in an electric field is QE. The force on a charge in a magnetic field is QVB. So E over B is V. And so that's how you get the velocity. What happens is if it's going too fast, FB is greater than FE. Too slow, FB is less than FE. If it's going too fast, it will slam up on the right side. If it's too slow, it'll slam on the left side. And opposite for this.
Does that create friction?
There's no friction in this. So there's no air friction. It would just be a vacuum and the particles would travel down. So this is typically what's set up in your particle spectrometer to get the mass, because it's circular motion. So in this particular case, it's mv squared over r. In this case, there is only a magnetic field. So this becomes QVB. One of the V's cancels. And then M is QRB over V, or QLB over 2V, because R is L over 2. So you can determine the mass. This V, if we set things up and are given that information, comes from this. E over B is V, that V goes there. We can get the mass if we have everything else. And so that's the example of how you can get specific particles of a specific not particles of a specific velocity to go into this thing. How do you know a particle has a specific velocity? Well, you've set that up beforehand. And so that's one of the things that people need to start thinking about is who uses particle spectrometers? Chemists, pharmacists, doctors, all sorts of people. And so this is how, it's a lot more complex than this, but that's just the general theory for it. And so that's number one. Number two, and in fact, I think number two needs to get fixed, maybe. Now, I1 has a current running from right to left. And let me make sure. And actually, I'm going to change this. It's going to go from left to right. I need to make a note of it in the thing. There is a current running in this loop, and it's running clockwise. Hold on, let's see. Yeah. Okay. Now gravity is pulling down. And with these currents all set up, the coil or the loop levitates. Which means that the sum of the forces vertically is 0. Now one of the things, and this loop is fixed, this loop is the one that levitates. The first force that you deal with is the mass of the loop times gravity, and it's going down, so it's minus mlg. This particular loop, current to the right, using our little wrap rule, the B field is out of the page above the loop and into the page below the loop. These wires see the B field of this current. Now these particular stretches of wire are not important because there's no magnetic force on these loops. We could go over that later. But there are two forces. I cross B, the force on this wire is up. This current is to the left. I cross B is down. So this is the force on the upper wire. This is the force on the lower wire. So plus F sub U minus F sub L. Now what are these forces that we're talking about? Well, F sub U is I2 L, and I think I may have had to give you this length. Oh, I definitely need to give you this length. That's the length. And then this is R1, and this is R2. So I2LB at the upper part, and the force on the lower is I2LB lower. The force on the upper wire is the current running through the wire I2 times its length times its B field at these points. Force on the lower wire is I2 again times its length times the B field at the lower part. Well, the B field at the upper part is mu naught I1 over 2 pi R1. And the B field at the lower is mu naught I2 over 2 pi R1 plus R2. And actually this is, once again, 1. So this 0 is minus MLG plus I2 L mu naught I1 over 2 pi R1 minus mu naught I1 over 2 pi R1 plus R2. And really what I'm going to do is, to annoy all the people who want their numbers, I'm not going to give you that satisfaction. solve for I1 as a function of all of those other variables. So I want a function, and basically I'm going to write it out for you guys right now. Mu naught R I1 or I2 ML, all that stuff. So MLG is equal to I2 L mu naught I1 over 2 pi R1 minus mu naught I1 over 2 pi R1 plus R2. Factor stuff out. MLG, because really the numbers don't matter, it's just the oh, and what did I forget? F lower is I2LBL. BL is this. So this needs another I2L. So really the I2s are the same because it's the same current going through the wire. The L's are the same, it's the same length. But the B field changes. It changes from this to that. Now factor out everything that you can. Mu naught I1, I2, L. So basically the entire numerator divided by 2 pi 1 over R1 plus 1 over R1 plus R2. Solve for I1. And that's it. So the key thing about this is to set it up so that the mass force pulling down and the force on the lower wire pulling down matches the force on the wire pulling up. Because if the wire remains constant in position, the sum of the forces is 0. It's in translational equilibrium. So really, then it becomes the question of, well, what are the forces? Force on a wire, ILB, upper wire, ILB upper, lower wire, I2 again, LB lower. Well, what's the B on the upper? It's this. What's the B on the lower? It's that. You assemble it, you identify that you know everything. I would have given you everything except for I1, and then you solve for it. The reason why I'm not plugging in numbers is most likely I'm not going to be able to. This is how I put together problems for tests. I do everything in letters. I put this in a spreadsheet, and then I just sit there and I play with the numbers until I get something that I like. So it's, in this particular case, this is a physics problem. Given this set of variables, find I1. And that's it. Now it's just a case of plug and chug. You guys do that all the time. That's not physics. So that's it for number 2. What's R what? R1 is the distance from this wire to the top or upper. R2 is the total width of the rectangle. I'm not going to give it to you. Because what I want is really, I want you guys, just copy that down. But what would really help you guys to do is go through there and go, what did he do when he went from this step to this step? Sum the forces vertically to 0. Identified his forces. ID'd what those forces are. They need magnetic fields, so I ID'd what those magnetic fields are. And then then it's just a case of algebra where you plug everything together. No numbers. No numbers. It'll just be letters.
On the test?
No, I'm not going to do that. On the test, I would probably... Definitely if I did this on a test, I would give you numbers. We're not... One of the things that... if I could, technically on a test, but we haven't had that much practice with it. We're always... You guys are so focused on numbers. If I threw an actual... Give me the function as a... give me this value as a function of all these other letters... It would be like a whole bunch of popcorn in a popcorn popper, and then people would just fall over and die. I don't think you guys are emotionally prepared for that. So, but stuff like this happens. Like as an undergrad, people would just give me a whole bunch of things and go, where are the numbers? There are none. Okay. And then you just crank it through. So. And plus, I got to be gentle on number 2 since I got the current flipped and I need dimensions and stuff. Skip 3 and 6, number 4.
Would that be the answer?
Yes. That's it. A lot of times in physics, you solve for an equation, and then that's it. And then you leave it to the engineers to figure stuff out and get numbers. That's what we do. So for number 4, have a wire here. You have a mass on this end. Magically, a current comes in that direction. The mass of the bar is 2 kilograms. Oh, and I'm hoping this thing works. It's a fulcrum. Yeah. That length is 2 meters. That length is 0.4 meters. The B field is 2 Tesla into the page. So with this fulcrum, there is the force due to gravity, which is that M times G. That distance is 0.4, and we'll call that R1. The center of mass of the bar, which means that distance is 0.5, which means that distance is R2, which is 0.1 meter. This is the center of mass of the bar. Now, the mass of the bar is 2 kilograms. I'll call that M sub B. Now, one of the things that I have to be careful about is describing this next part. Ideally, this current is going to the right, or at least that's what I say. I cross B, since it's into the page, is up. So the magnetic force on the bar, which is, you can centralize it at the center of mass, is ILB. The question that people would ask is this thing moving? Answer, no, stationary, never moving. Excellent, love when things don't move. So you can go sum of the torques is equal to 0. It's not rotating. In fact, you could do this one of two different ways. The first way, we'll do sum of the torques. What did I use? What? The length of the, oh, actually, whoa. It would be more. I thought the bar was 1 meter long. So if that distance is 0.4 and this distance is 1, then this radius must be 0.6. So it's not to scale. Let's draw it to scale. No, thank you. This makes it appear a whole lot better. Now, well, the B field is into the page because I say so. I is to the right, B is into the page, the resulting force is in that direction. Ah. Which actually,
You just switch the direction.
yeah, because it's, this is Eschenberg's left-hand rule, because no matter how you look at it, it's still
Great.
Little Joe. Can't be funny on a Friday afternoon and no candy. So, whenever I think about, because see, sometimes I pull out my left hand and I look at it, because originally, how do you remember as a kid which hand was your left hand? You look at, you hold your fingers up like this, and your left hand spells it out. Oh, and then someone told me the joke that this is the loser rule, or you're a loser in 3 dimensions. No matter how you look at it, you're still a loser. So that's switch it to the left hand rule. So the sum of the torques is equal to 0. I think we got time, so I might as well explore. MGR1 to the left, down, out of the page, positive. This force is to the right, right, down, into the page, minus. That force is to the right of the fulcrum, up, out, plus FB R2. So 0 equals MGR1 minus MBGR2 plus ILBR2. The force, magnetic force on the wire is ILB, and then you multiply it by the distance from the center of mass of the bar to the rotation point. And now you solve for I. MBGR2 minus MGR1 is equal to ILBR2. So now G MBR2 minus MR1 divided by LBR2 is equal to I. Now, one of the things that could happen, and this may be the case, actually, we're going to do this numerically right now, is if I is negative, that just means that the current wasn't running from left to right. It should be running from right to left. So if the I that we get is negative, we know that the current's going in the other direction. So G is 10, MB is 2, R2 is 1. No, R2 is 0.6. M, that particular M is 0.2. That R1, 0.4. I think we are going to get a positive. Yay, positive. Length is 2. B is 2. R2 is 0.6. So we are getting a positive number. And the current is 4.67 amps. It's a lot of current, but hey, it's a number.
So if we had gotten a right to left current, then we would,
This I would be negative.
we would flip the FB. So that
Well, really, what would happen here is, let's say, for instance, that the I was negative. Then you would just say, I thought the current was going from right to left because the I is a negative number. It's 4.67 to the left. That's it. And then stop right there. You don't need to recalculate.
But I mean, in actuality, in reality, correct?
Yeah, if I did this problem and I went back and I said, now I'm going to prove it, polish it, and because this problem set is kind of a throwaway. Let's just play. I would go back and then I would flip the current to the left, so there wouldn't be this. And so that's it. It's just a set of conditions. If I had gotten a negative number, I would have realized I made a mistake, and I should have drawn the arrow to the left. But it was positive, so I must have fixed it early. Because when I write problem sets, a lot of times I just do this going, I want to see if they can get this. And I don't put much thought into the numbers. For test level problems, it's ironclad. It's pretty certain. All right, page 2, number 5. Number 5 is a fun problem. Uh-oh, he said fun. This problem has history. This problem was given on a test. And let's talk about it. I1 is 50 milliamps going from right to left. This guy is going from left to right. I2 is way bigger than I1. The distance between these two things is 0.005 meters. So that's the distance. I want to know where the B field is 0 between these lines. Now, whereas, why did I get rid of 3 and 6? It's way too hard for the test. It's just not, it could never, it would just be the only problem on the test. 2's kind of sloppily done. So I'm not, that's something exactly like this wouldn't be on it. 4, it's a legit problem. 1, the discussion of the particle selector, the discussion of the particle spectrometer, that's legit. 5 is very legit. Would it be, am I guaranteeing it's on the test? I don't know. I won't know really until, hold on. Let's do this. I have no idea if it's going to be on the test. Am I lying? So I really won't know until, I know you guys, if I told you in the review session that I had written the test, you would hold me hostage until I released the information. So for the problems, I wait until late that night.
I'm gonna tweet you at like Wednesday, like noon.
First thing that you would do with a problem like this is label the directions of the B field. Everywhere. Now, there are 3 major regions. There's the upper region. There's the middle region. There is the lower region. 1, 2, and 3. Red is going to label the magnetic fields from the upper line. Since the current is going from the left, the magnetic field is going into the page above and out of the page below. Regardless of how far it is below, it's still coming up. So there it's up, there it's up. Here it's going to the right. So I will label it in green. B field coming out of the page above and into the page below. Yeah, the wrap rule. For the wrap rule, like think of this as the wire. The current is going up towards the ceiling. So for the wrap rule, some people say it's the right-hand rule. Technically it's not. I used to say the second right-hand rule. That's confusing. The wrap rule doesn't make sense. You put the current, thumb in the direction of the current, and then you wrap your finger. So think of this as a plane. Current, my fingers are coming at you on that side, so circle dot on that. And when it curves around, it goes into the page on the right. And that's it. Now, let's talk about this for just a moment. Where is it obviously impossible to not be 0? 2. It cannot be 0 in 2. It is impossible. Why? Both are out of the page. So only in regions where they have to be opposing each other. Now, the other thing is it can't be 3 either. And why is that? Because, yeah, just think about this point right here. If you're this close to a wire with such a greater current than the other, the B field from the lower will be greater than the B field from the upper, because you're just closer to the wire. The further out you get, BL will always be greater than B upper, because the wire that is closer to the point has the greater current, so it will always have the greater B field. So it will never be in section 3. Now granted, at distance infinity, the B field would be 0, but that's not a point that we're interested in.
What about at distance 0?
At distance 0, you're dead set on the wire.
On the wire.
That's not going to be allowed. It has to be a region not physically touching a wire.
Do particles flowing through that wire, electrons, protons, do they feel from the first wire?
They do, but they're going to feel forces, but I'm not asking about forces.
So you said the lower the wire, no matter how far you get,
Yeah. So the region that's adjacent to the stronger wire, that region cannot have a B field of 0 within it, except at very large distance. So the only region we're interested in is number 1. So what we do is, I say that the distance from the upper wire to the point where B is equal to 0 is X. So the B field at that point is 0. So minus the B field from the upper plus the B field from the lower. So the B upper is equal to B lower. The B field of the upper, mu naught I upper, instead of 1 and 2, I'm using upper and lower. Mu naught I over 2 pi x equals mu naught I lower divided by 2 pi x plus d.
Dr. Can you explain why in some of the beats, negative B upper and positive B lower? Is that
The B field for the upper in this region is into the page, so therefore negative. The mu naughts and 2 pi's cancel. So I'm left with I upper x, I lower x plus d. Now I've got to solve for x. Now there's a little bit of algebra. I just multiplied everything by -1. And so you get this. So I upper is 50, D is 0.005, I lower 800. As long as you're using milliamps and milliamps or amps and amps, it doesn't really matter. 800 minus 50. You could even use millimeters.
Why did you say multiply by
Do what?
multiply by negative ones, just isolate the I?
Well, I wanted to end up with a positive term. I mean, a -1 would have canceled out anyway, eventually. So I get 3.33 times 10 to the -4 meters. Now, what's so interesting about this particular problem was when I gave it to the class, there were 3 distinct groups. One just got it wrong. The other group got it right and did it the way that we did. And then the third group was actually the most interesting group of them all. Because what they did is they said, I think there's a second point here. And what they did is they said, rather than going into region 1, they set an X that was actually in region 3. And what was interesting is that what happens is that the math produces, I believe if I recall correctly, it produces an X that looks like this. So basically it flips the currents. So if IL 800, D is 0.005, I upper 50 minus 800, there's a whole derivation for this.
They switched the magnitude of the 2 wires.
Yeah. But this is the interesting point that so they actually got -5.33 times 10 to the -4 meters. Then that third group fell into 2 categories. So this is the lower, this is the 800, this is the 50. They said it was down here and then they got a negative number. Half of that third group just freaked out and quit. The other half looked at this number, and this was the group that I was more proud of than the people who got it right to begin with. They said -5.33. If I treated this as the positive X direction and I got a negative number, then in reality it's in the opposite direction. And what's the distance here? 0.005. And what's this distance here minus 0.005? 3.33 times 10 to the -4. The math took them right back to the correct place. They were able to interpret what that negative number meant. Just like in the previous problem, had the current been negative, then I would have said, well, then the current's now going left. Had I chosen the incorrect region, I would have gotten a negative number. But then I would look at it and go, well, maybe if this is 0 and that's positive, I need to go in the other direction. And it takes you right, the math literally takes you right back to the correct place. So it was this special group of the third group that I was most impressed. I had no idea that this was going to happen. And it was interesting to watch 200 students break down into all these different groups and see how it behaves. And so that's the part. So I'm done. Yes. And I'm sorry, because of the fan, I can't hear. Yes. Yeah, in fact, it doesn't really matter, because in the numerator, what's the numerator? Milliamp. What's the denominator? Milliamp. Milliamps divided by milliamps is nothing. So as long